It's in the morning. You have just made a cup of coffee waiting for it to cool down a little bit. When you put the cup of coffee on the table, the temperature is T initial and the temperature of the room is T room. But you know that the temperature of the coffee is decreasing because you have experienced in your life that whenever you wait enough for the cup of coffee, it gets cold, which is how it feels when the cup reaches the temperature of the room. These two temperatures are constant, but this one is a variable. It changes. And change is what lies in the heart of calculus, even in the morning when the sun is shining on your hot coffee. Newton has a law of cooling that is expressed as the sum of the room temperature, which is the final temperature of the cup of coffee, and an exponential term that shows at which rate the cup cools down. This expression is another form of saying if we wait enough, the temperature of the coffee will reach the temperature of the room. This is the concept of limits. Before talking about limits, let's take a closer look at these two words that lie in the heart of this concept: infinite and infinitesimal. Infinite stems from the Latin words in, which means without, and finitus, which means limit. It means without limit or without boundary. We use this word when we want to talk about extremely large or infinitely large amounts, larger and larger, as much as you can go. Infinitesimal was coined in 17th century by mathematicians to talk about the very small amounts. It means infinitely small, and we show it by a variable that goes to zero. It is becoming smaller and smaller as much as your imagination can go, but not reaching zero. In fact, we are still dealing with the concept of infinity in another way. To get a better feeling of the concept of limit, let's take a look at this power function y equals x squared. At this point A, we are looking for the tangent line that touches the curve at point A. We call the slope m. Now consider another point which can be varied. It means we can change it, slide it if you wish. It is not a constant. Let's call it b, and its components are x and x squared. The slope of the line connecting A and B is MAB, which is different from m. We can write the slope of this line as x squared minus 1 divided by x minus 1. Here comes the magic of limits. The tangent line to this parabola at point A can be calculated if b gets infinitesimally close to A, or in other words, as b approaches A. If you take a look at the diagram, you can see that it happens if x approaches 1. We can write the numerator as x plus 1 times x minus 1. As x minus 1 is a very small number, as x gets closer to 1, we can simplify the limits and find a tangent line to this curve to be 2. In this example, point B is approaching point A from the right, making x minus 1 an extremely small positive number. If we approached A using another point like C, it would be an example of approaching from the left. In this case, x minus 1 would be a very small negative number, as x would approach 1. Now suppose that we have these two functions. They are the same actually, but something is different at x0. The limit of function f as x approaches 0 is 0, and also the value of the function at 0 is 0. In the case of function g, the same limit is again 0, but the value of function at this point is 2. So we can see that the limit of a function at a point is not about that function, but about approaching the point and seeing how the function behaves as we approach it. This function is continuous at x0, meaning that at x0, the limit of the function is equal to the value of the function itself. But this one has a discontinuity at x0 because the limit of the function is not equal to the value of the function at this point. Now let's take a look at this function. This is sine of pi divided by x and really seems messy in the middle. What is the limit of the function as x goes to 0? This argument changes more rapidly as we approach 0 and gets larger, so there is no specific point that the function reaches. In fact, the limit does not exist in this situation, and no matter how we get close to 0, the oscillation between minus 1 and 1 gets faster and continues to infinity. So we don't have a limit here. Let's look at another function. This is the Heaviside function. It is widely used in engineering, physics, control theory to model systems that switch on at a specific time or sometimes a threshold. What is the limit of this function at x0? If we approach 0 from the right, as we get close to 0, the function goes to 1. But when we get close to the function from the left, the function approaches 0. These two limits are not the same, and we get two different values for the limits depending on whether we are approaching to the point from the left or the right. So the limit does not exist in this case. So when we get arbitrarily closer to a point on a function, the value we approach is called the limit of that function at the point. I say arbitrarily because it doesn't matter whether you approach this point from the left or right. In both cases, we have to reach the same value for the limit to be meaningful at this point. Another important concept here is that the limit of the function has nothing to do with the value of the function at that point. So if the limit of the function exists, meaning that the right hand and the left hand side limits are equal and also equal to the value of the function at that point, we can say that the function is continuous at that point.